Oh.
All right, here's where we are. Okay, so we've discussed two timelines of things going on, right? We've got Dalton to Thomson to Rutherford, right?
Yeah.
So the important thing there, Thomson found the electron, Rutherford found the nucleus. Okay. Then on the other side of the timeline, we have people studying light. Okay. The big things that happened with that we need to know about are Planck discovered the concept of quantized energy. So energy exists in little quantities that are equal to the constant that's named after him times the frequency. Okay. All right, he came up with that. Einstein expounded upon that and used that idea to explain the photoelectric effect. And it gave us the concept of a photon, which is a massless particle, and the idea of wave-particle duality, which he said light is both a wave and a particle, albeit a massless particle. Okay. And the photons of light carried a energy that was equal to Planck's equation. Okay. All right. That brings us up to where we are now. Okay. So those two timelines are now going to converge. Well, first off, did we do this last night?
Yes.
Yeah.
Okay. I made some adjustments this morning because I realized I didn't do a very good job being specific about the significant figures. So I tweaked it just a little bit. Didn't change the overall answer, just changed where things were rounded to. And I went back and added some stuff in the front column so that you would know to start that we had three significant figures. So anyway, kind of fixed that up a little bit. Yep.
I had a question about last column number 5.
Okay. The violet one? No, ultraviolet? Which
Yes.
one's 5? Yeah, ultraviolet. All right.
Why are 3 the 2 above it to the 0 and then the ultraviolet one is to the first?
That's just me being overly scientific.
Okay.
You don't have to put 10 to the 0 because anything to the 0 power is equal to what? 1, right? Anything to the 0 power is equal to 1, so that's really being kind of obnoxious on my part.
But then 10 to the first means.
That means it's 41.4.
Okay.
In expanded notation. Yeah.
Thank you.
All right. Everybody good with that?
Yes.
Okay. All right. All right, hit the lights for me on this next couple of slides. It'll look a little better if we got the lights off. If anybody sees my laser pointer anywhere, I'd like to have it back. It's disappeared. But anyway.
First period console.
Yeah, I don't know if they got the energy. I'm leaning more towards 7th period.
How many chemistry classes do you have?
I have 2 regular chemistries and an AP chemistry,
What else do you teach?
AP physics, and environmental science.
All the sciences.
Just about. All right.
What's your 7th period?
All right, so Niels Bohr is about to come along, okay? He's going to try to explain something called bright line spectra, which we're about to explain. But what he ends up doing is taking Thomson's electron and Rutherford's nucleus, Planck's quantized energy, and Einstein's photons, and taking all of those ideas and putting them together, okay, in order to explain something called a bright line spectrum. First off, we need to know what a continuous spectrum, what does that look like to y'all?
Rainbow.
It's a rainbow, okay? So physicists call rainbows continuous spectrums, okay? Or continuous spectra, to be plural, okay? So what is a rainbow? Well, it's all the photons of light, okay? So if you've got all the possible frequencies together, we see that as white light, okay? If you take that and pass it through a prism or some other medium at an angle, then those photons that are all traveling together will separate based on their wavelength. When it bends through the prism, they spread apart because different wavelengths will bend at different angles, okay? So that separates it out into all the different photons, and we see this continuous band of ever merging into the next one color, right? Okay. Now, let's different though if you look at a single element's emission spectrum. Okay, it won't look like that. So let's flip the slide here. Okay, if I take hydrogen, just a tube of hydrogen gas. Everybody ever seen a neon sign?
Yes.
Okay, so relate this to something practical here. So a neon sign is made of this glass tubing, okay, that they can shape in whatever they want it to say or whatever they want it to look like. They fill it full of neon gas, okay, number 10 on the periodic table, right? They fill it full of neon gas, and they pass electric current through each end of it, all right? And that makes it, energizes the atoms in that neon, and it starts to glow. Everybody with me? Okay? All right, so you can do that with anything, just about, all right? If you use hydrogen, for example, if you just put hydrogen in a glass tube, and that's much more dangerous than neon. When you break a neon sign, nothing's going to happen to anybody because neon's non-reactive. If you broke a hydrogen sign, it's going to explode, so you wouldn't want that. But if you have hydrogen in a glass tube and you heat it up, it's going to glow a pinkish looking color, okay? If you look at that through a prism, what you're going to see is not a continuous spectrum, but you're going to see 4 distinct colors. Bright line spectrum, we call it. See? So if you took a glass tube of hydrogen, heated it up, looked at it through a prism, you're going to see 1, 2, 3, and that was hard to see, but 4 lines. Okay? And that's it. That's all you see. It's just those 4 lines. It should be black in between, but this has got a little bleed through from some background light or something. Let's get this picture. Okay? So that was a phenomenon that was known for a long time before Niels Bohr ever came along, but nobody could explain it. Very similar to the photoelectric effect. Everybody knew about it. Nobody could understand it until Einstein came along and explained it. All right. So here's his explanation. It takes us a couple of slides to explain all this. Okay.
Yes, you can.
Yep.
They were just outside your door looking at.
Where are they? You know, they'll be okay.
I'll catch you later.
All right. So Niels Bohr discovered that bright line spectra were caused by photons with certain energies. So he's taken that idea from Einstein, that those 4 lines that we can see are coming from 4 distinct photons of certain 4 particular energies. The energy is coming from relaxing electrons. That's the term we're going to use, and we're going to draw a picture of this. All right. The relaxations are the result of excitation. So electrons undergo what are called transitions. Okay. So electrons are always transitioning. They get excited and then they relax. That's fancy words for saying they go up and they come back down. They go up and down, up and down, up and down. If you put energy into an atom, the electron goes up. When it comes back down, energy has to come back out. It comes back out in the form of a photon. Okay, energy in, electron up, electron down, energy out. That's the process, right? The energy of that photon is equal to the difference in the energies between the transition levels. Okay, we're going to see a picture of that in a minute. That won't make much sense probably until we look at a diagram. And we're going to actually do some math with it. Well, you probably will tonight. But one more slide here. Y'all still writing?
Yes.
Okay. Oh, right, faster. We'll have a book. Doesn't have to be legible, just write it down.
How am I supposed to study it?
It's that does defeat the purpose there. All right, we're good. Y'all do have access to the PowerPoint. Y'all could just look at it
Yeah, but
later.
don't get behind.
I know.
Right. None of them are talking.
And
I
then we start
appreciate
writing
notes.
I appreciate the class engagement. I really do. But sometime today we have finished it.
We have plenty of time.
You just go
They
home
don't.
and write together.
We don't have plenty of time, but it's what it is.
5 minutes.
Okay, here we go.
Oh no.
No.
Ah, I'm sorry, write that down. I wrote that 5 times. Just good grief.
Gabby, where are you at?
I'm on the last like 4 words.
Sarah, where are you at?
Oh, I got my Chromebook open.
Oh. So where are you at?
Electrons get excited.
Oh, you're kidding.
I have my Chromebook open. You can go, Mr. Taylor.
Okay, I
No.
can go.
No.
Wait, I'm only on electron transitions.
Y'all
Bro.
gotta go. Y'all gotta go. I gotta go. man.
Brandon is slow.
Yeah, like
gonna-
actually, but go ahead.
You're gonna forget what we're talking about by the time you get it wrote
I'm not
down.
ready.
Yeah, just go.
No.
I was reading.
Wait, close
Alright.
it, Brandon. She said wait.
Formula of the hydrogen atom. Here we go. Some fun facts, okay? All right, so here's what Niels Bohr said. Hydrogen has a positive nucleus. He got that idea from Rutherford, okay? Hydrogen has 1 electron. He got that idea from Thomson. This is sort of Planck's idea coming up next. The electron can be on 1 of 7 energy levels, not anywhere in between, okay?
Wait.
1 of 7 energy levels.
So either 1, 2, 3, 4, 5.
1, 2, 3, 4, 5, 6, or 7. That's it.
Then 1.5.
No such thing. It's not allowed to use quantum mechanical terminology. It is a not allowed value. So the n equals 1, 2, 3, 4, 5, 6, or 7. That n is called a quantum number. The electron spends the majority of its time in the ground state, sitting on the bottom at the lowest level it can be. That's n equals 1. And it'll stay right there until something bothers it, okay? So that's where it wants to be, is on the ground state. It would like to stay there. Things like to be balanced and at the lowest possible energy. That is a fundamental principle of nature, okay? So it wants to be at the n equals 1 ground state. But if it gets excited because something energized it, then it'll go up to 2 or 3 or 4 or 5 or 6 or 7. One of those 6 other possibilities. When it gets there, it stays about some fraction of a nanosecond, and then it falls back down. Anybody ever fallen down the steps?
Yeah.
Okay. If you fell down the steps more than once, the second time won't be like the first time, and the third time won't be like the first or second time.
Right.
You're going to hit on different places, and you're going to bounce, and sometimes you're going to skip steps, and it's each time you hit, you're releasing some energy, right? It's painful. Okay. Well, when that photon relaxes, it might not go 7, 6, 5, 4, 3, 2, 1. It might, but it might go 7, 5, 2, 1. And the next time it might go 6, 5, 4, 1. There are all kind of random possibilities. But every time it hits on an energy level, it spits out a photon. Okay? A little photon comes flying out of that atom. Okay? That photon is going to have the same energy as the difference in energies between where that electron fell from to where it fell to. So it falls from a high place to a low place. The difference in energies between those two places is the exact amount of energy that comes out in that photon. This model he came up with works perfectly for hydrogen. Does not work for any other element. He knew that, which means he knew he was onto something, but didn't have the complete answer. Okay. Let's draw a picture on the board. Light's coming back.
Okay, so.
All right, here's the positive nucleus of a hydrogen atom. We now know that that consists of one single proton. You didn't know that. Okay, you haven't figured that out yet. All right, so here's the nucleus, right there. It's got an electron. According to Niels Bohr, that electron is going around in a circle, just like a planet goes around the sun and the moon goes around the earth. Okay, he was incorrect about that. Okay, that's what he thought. And that thought works for hydrogen, but it doesn't work for anything else. And he said, well, it could be on that orbit, or it could be on this orbit, the second one, or the third one, or the fourth one, or the fifth one, the sixth one, or the seventh one. Okay? So if that electron gets excited, it can jump up levels. It can jump to any of these other 6 levels. Let's just say hypothetically that it goes to the 6th level. Okay? Some fraction of a second after it hits there, it starts to fall back down. Okay? If it hits here first, here comes a photon. And then it hits here comes another photon. And then when it hits back on the ground state, comes another photon. Okay? So it transitions up, we call that an excitation, and then it immediately transitions downward, we call that a relaxation. And every downward relaxation, photon comes out. Okay? All right? Get the idea? What goes up must come down. You ever stood at the bottom of the steps, throw the ball up the steps?
Comes bouncing down.
Did it come bouncing down? Does it bounce back down the same time every time? Usually not. That's kind of why it's entertaining little kids that do stuff like that, because it's kind of erratic, right?
I still find it entertaining.
Might. Okay. Very similar idea. Okay. The only difference is you have to be careful thinking of this like a staircase. Okay. Because the gaps are not the same. So a staircase, if it's built correctly, the height of each step is the same, right? The differences here are not the same. So the gaps get closer the higher you go. So the largest gap is between 1 and 2. The smallest gap is between 6 and 7. Okay. If you go past 7, you get into theoretical physics, and the gaps keep getting smaller to the point that they become basically indistinguishable. So that's why when you end up being something like a person walking around, you're on some almost infinitely high energy level. So when you jump from one energy level to another, it seems seamless. You don't seem to be a gap because the gap has gotten ridiculously small, down to the size of like Planck's constant stuff. Okay.
But I really don't know what to talk about. It's like so cool to listen to it.
Huh?
It's like so cool. But I
It's
have
cool to
not-
think about it. You just have to ponder it, man. You just have to ponder. All right. Skip ahead just for a second. I'm going to show you a picture right here. Okay.
Penny has a question.
Yes.
So when you say for us, it's like so small that it's like seamless and stuff, how, I don't know how to say this, where in us, if that makes sense?
You as a object.
Okay.
Like if you were walking and then you started running, right?
What did
Okay.
I say?
So you're walking and you start running. You walk, then you jog, then you run, then you sprint. You come back to a run, and you come back to a jog, you come back to a walk, and then you stop, right? Okay. You're going to feel like you just sped up on a nice smooth curve, right? Okay. Because as you're getting faster, your energy is increasing, your kinetic energy is increasing,
Yes.
and it's jumping levels, but the gap between those levels is ridiculously small. There's no way that human senses can perceive that. Okay, it's down there on the level of that Planck's constant number, that kind of small, right? But if you were an electron and you got yourself a little excited and started moving a little faster, then you're going to notice that you jumped somewhere and that you never were in between the two places. You would definitely feel that if you were an electron. But you're not. Yeah. All right, if you look at this right here, and you don't have to know these names that are up here. That's not, you don't have to know that. All right, what we do need to know is that of all the possible transitions, okay, so you can go 7 to 6, 7 to 5, 7 to 4, 7 to 3, 7 to 2, 7 to 1. You can go 6 to 5, 6 to 4, 6 to 3, 6 to 2, 6 to 1. All the possibilities, right? Okay. There's only 4 of them that give a visible photon. We do need to know this.
Oh, is this how you make colors? No?
Yes,
Okay.
but sort of.
Yeah,
Okay. So 6 to 2 puts off a photon that we can see. Okay. 5 to 2 puts off a photon we can see. 4 to 2 and 3 to 2.
So it's like 2, like a special number?
No, it's just what the energy gaps happen to be, that the photon is a frequency that our eye understands. Yep. If anything falls all the way back down to 1, no matter where it starts, that's too much energy for our eye to see. That photon's going to be ultraviolet. Okay. So it's coming out, hits our eye, burn our eye, but we won't see it. Our brain doesn't interpret ultraviolet light. Okay.
Is there
All the
glasses-
rest of them, do it now?
Is there glasses that like make us like see it?
Not really. No. No.
6 to 2, 5 to 2, 4 to 2, 3 to 2.
6, 5, 4, or 3 falling to 2. That's the 4 visible photons. Anything falling to 1 is ultraviolet. All the rest of them are infrared. So all the rest of them are less energy than our eye can comprehend. Okay. Everything falling to 1 is more energy than our eye can comprehend. There's only 4 transitions in hydrogen that produce photons that our eye does comprehend. Okay. Meaning it causes a chemical reaction in our eye that sends a signal to our brain. The rest of those photons just get absorbed or pass through us or whatever. Go back up now. There you go. The following relaxations result in visible light photons. Now this is only hydrogen, okay? Only hydrogen. The visible light photons and helium and other things come from other transitions. But in hydrogen, it's 6 to 2, 5 to 2, 4 to 2, 3 to 2. That's probably a test question. Everything else is either infrared or ultraviolet, meaning too low of energy for us to deal with or too high.
What is infrared?
Anything
Like, I've heard of infrared.
less energetic than the color red. So it's a longer wavelength than red.
So what's the infrared beam?
yeah, go back.
It's a beam of photons that
Infrared?
have a wavelength longer than what you can see.
And ultraviolet's one is has too much frequency.
Yep, ultraviolet's wavelength is too short for you to see.
So like 7 or 6 or 7.
Yeah, anything falling down to 1 is going to produce an ultraviolet photon. Okay. All right, this got a little cut off. Okay, there's a 7th one down there. If we exit out of that, you can see there's 7. I can't get that to adjust, but anyway,
The green dot.
well, I ain't got time to mess with it right now, but anyway, we can see the first 6 and that's fine. So Niels Bohr came up with an equation that would figure out the energy of each of the orbits, okay?
We need to write down this equation.
No, hang on, just, that should say orbits, that should, I'll never be able to see this. I am gonna fix this, 'cause that's gonna help it out. That should say. Okay, now, so these are the energies of each orbit. All right, 1, 2, 3, 4, 5, 6, and 7's off the screen, but we'll be fine without it. Okay, in both joules and electron volts. Okay, so this comes from that equation at the top. So it's remarkably simple considering how complicated this is, what all he had to do to figure this out. It comes down to something that's almost ridiculously simple. It's this number, 2.18 times 10 to the negative 18, divided by the square of the energy level. So 1 squared is how much? 1, right? Good. So the energy of orbit number 1 is this number divided by 1. Same number, right? Orbit number 2 is this number divided by 4. Why 4?
2 squared.
2 squared is 4. Then you divide this number by 9, this number by 16, 25, and 36, and 49. Okay? And that gave the orbital energies, the orbit energies of each of the 7 levels in a hydrogen atom. Okay? Where he came up with that number is a little bit complicated. We won't get into all that. But it all simplified down to simply a number divided by the square of 1, 2, 3, 4, 5, 6, or 7. Could have been a lot worse. All right. Real quick, before we flip the slide, and we'll have to flip back and forth, quickly write down, let's write down number 2 and number 6. We're going to do a little math with that. Okay. So write down energy 2, energy of the 2nd and the 6th energy level of hydrogen. So energy level 2 is negative 5.45 times 10 to the negative 19. And the energy of level 6 is 6.06 times 10 to the negative 20. Jot that down right quick, just so we don't have to flip back and forth. When you're home doing your homework tonight, you can flip back and forth. All right. Delta E, the change it, right down. Here we got flip back. Got it? Now we got it. All right. The change in energy for an electron is equal to the absolute value of its final energy minus its initial energy. What do we do? What's the absolute value mean? Just drop the negative. After you find the answer, you drop the negative, right? So we're looking for the absolute difference between the 2 energy levels that the electron was on and ended up going to. That's the energy change for that electron. That's going to equal the energy of the photon that comes out, okay? So we can find the frequency of that photon using Einstein's equation that he borrowed from Planck. So that takes us to this slide, okay? It's kind of all messed up too, but anyway. All right, here's our 4 visible transitions, 6 to 2, 5 to 2, 4 to 2, 3 to 2, okay? Tonight, I want you to calculate the energy change of each one, the frequency of the photon that comes out, the wavelength of the photon that comes out, and then look on the couple of slides down, and there's a chart that tells you wavelengths of various colors. See if it matches up. There's a red, a blue, a bluish green, and 2 violet photons. Okay, let's do the first one. All right, quick. What time are we out here today? Ashby Day. What time? 37? I got 10 minutes. Yeah, we can do the first. First period didn't get to do the first.
And then participate.
Okay, so when n equals 2, the energy is negative 5.45 times 10 to the negative 19 joules. Okay. When n equals 6, the energy of level 6 is negative 606 times 10 to the negative 20 joules. All right, so when an electron in a hydrogen atom falls from right there down to there, right? That's happening, right? 6 to 2. Okay. Out comes a photon. All right, what's the energy of that photon? Well, it's equal to the change in energy of the electron, which is going to be E2 minus E6, absolute value.
Where,
Final place minus the initial place.
where are you getting these equations? Like, how do you
It's on the previous slide.
Sorry.
Oh,
You just had it up.
Right.
Okay, never mind, sorry.
Actually, Niels Bohr and I had lunch one day.
Yeah.
He slipped it to me on a napkin. I'm the only person who knows this. All right,
That would be pretty cool.
would be. All right, so negative 5.45 times 10 to the negative 19 joules minus negative 6.06. So here we go. We got to use our calculator correctly, right? We got to be able to enter scientific notation values, so we're going to get wrong answers. Just plug it in, right? That's all there is to it. Apparently, it's not that simple.
That's all we're talking.
Uh-huh.
You just do that bullshit, man.
Yeah.
Why?
You got a question?
Yeah, but just
Oh,
like
okay.
some numbers
Okay, so
together.
why are we minusing the, okay, so we know how it's 6 to the 2, why are we minusing the 2? Like, why are we minus the 6 from the 2 when you're dropping from the 6?
Final minus initial. So the final place that you hit is 2. It went initially from 6 and finally to 2.
Okay.
So it's final minus initial. Y'all check my math. I got 4.84
Oh,
It's 6 is
times 10 to the negative 19. Everybody else get that? I think type it in again. I'll type it in. I might as well. Y'all are slow.
Sandy got that answer. Sandy got that answer. Don't speak up.
There it is. All right, so that is the difference in energy between here, right? Between those two places in this hydrogen atom. That's the difference in the energy. So that electron lost that much energy. It lost it to this photon, okay? So that means that the energy of the photon is the same as this number. So let's just write that. That's the same as delta E, okay? Which is all going to be equal to Planck's constant time frequency. So the frequency of the photon is energy divided by Planck's constant. Everybody good with that?
the E photon is 4.84, right?
Yep.
And then it just equals everything. So,
Well, what is the after delta E? It's delta E is also equal to.
H nu, that's Planck's equation, or now Einstein's equation. So the frequency of that photon is 4.84 times 10 to the negative 19 divided by 6.626 times 10 to the negative 34. $7.3014. Who was confused at? Good with that number?
That's where I'm confused. I don't know how you got the 4 point.
Negative that, minus negative that, take the absolute value.
But minus,
Minus is
the
plus, yeah. Put it that way. All right, so that's the frequency. Wavelength, with the speed of light divided by that frequency. So that's 3 to the 8 divided by 3, 14. That's 4.11 times 10 to negative 7 meters, which is 411 nanometers, which is purple. So when your brain, when your eye, let me back up. When a photon with a wavelength of 411 nanometers hits your eye, it causes a specific chemical reaction that sends a specific signal to your brain, and your brain says purple. Click one more button, we'll see. Got it. 410, 411, whatever.
When I just did, the 4.84, divided by the 6.62, I got 7.30 times 10 to the negative 54th power. But I got the same 3 point.
You left off, you put, what did you do? You have you missed a negative sign somewhere on either negative 19 or negative 36, I mean negative 34. One of your exponents is not negative. So probably the first one.
It says negative 19. Then you can try to make it like,
How did you get the 4 point? 4.84.
And yeah, I got the same thing.
Put them in parentheses, the whole number.
Yeah, it's not
Which,
giving me
which those
4.84.
numbers are the four ones that were in the first chart, remember?
I'm getting 6.6 minus the 5 point this, and I'm not getting that number. I'm getting
Are you
0.6.
putting it in? You got 6.2.
I can't put it in.
And math.
You have to put that times 10 to the negative.
I don't have this. I just have to
Yeah,
make it easier.
I agree.
How do you do that?
Okay, let me show you one more thing right quick. This is not something to memorize right here. This is just for a reference
It's out
to,
of 15, man.
if you scroll down, or the next slide, look, this will tell you the ranges of wavelengths that are whatever particular colors. Please don't memorize that. That's just for a reference, okay? But you can see that 410, 411 falls in the purple violet range. All right. Oh, tonight, please do the rest of these. They're the answers, right? Please verify that you can solve all of those, okay? Please practice, practice, and practice.
It's just